Problem SAC16E involves a continuous charge distribution, and you're supposed to find the electric field. In this case, the charge distribution is strictly on the x-axis, and in fact, we're supposed to find the charge distribution on the x-axis at points to the right of the actual charge distribution. We're supposed to find the electric field at positions to the right of the entire charge distribution. Let's see if we can get a sketch going here. Take y-axis, x-axis, so we got a charge distribution extending from x is equal to 0, call that the x direction, up to x is equal to a, and the charge distribution is given by lambda is equal to constant times the position along the x-axis. I'm going to call the positions where the charge is x prime, and the position where we're trying to find the charge, that'll be at x comma 0. So for summing up all the contributions due to each of the little bits of charge, say a little bit of charge dq, taking up an infinitesimal amount of this charge distribution. We call that variable the x prime variable. So it's at a position x prime. We've got an amount of charge dq at a position at x prime. And then the place where I want to find the electric field, I'll call that x comma 0. Okay, so what's the game plan? I'll take the contribution to the electric field at this point due to that little bit of charge. I need a line that extends from that position all the way out to here. That'll be the distance r. And I'll get a contribution to the electric field dE due to this little bit of charge. It's strictly along the x-axis, but that's the only direction we have for the charge. It's along the x-axis, so I could think of that as dEx, but it's the total electric field. The dE is going to be the Coulomb constant. You can write that as 1 over 4 pi epsilon 0, but I'll call it K, times the amount of charge that we're dealing with, divided by r squared. Now I got to add up all those contributions from all the little bits of charge along this line that extends from 0 to a. But first off, I want to simplify that expression a little bit, or make some substitutions. The dE I can write as the Coulomb constant. dq is going to be lambda times dx prime. So I'm going to be integrating over x prime. And r itself, r can be expressed as the position where I'm trying to find the electric field minus the x prime here. That'll be the length of this. So it's from here all the way out to here minus from here to here. So minus x prime. So r squared is going to be x minus x prime all squared. And lambda itself is some constant times x prime. So that's saying that the charge is more bunched up over here And it's pretty heavy over there, and then it linearly dies down to 0 charge per meter over in this region. So we got high charge density up here, low charge density down on this end, where C is going to be some value that's got units of coulombs per meter squared in SI units. So that you multiply it by the value of X that you're at, and you got lambda has units of coulombs per meter, as always. So it varies, but we know how it varies. It varies linearly. So that's a specified constant, or unspecified constant actually, times x prime dx prime, all divided by x minus x prime, quantity squared. So now I got to sum all that up. I'll just call it the integral of dE on that side, the sum of all the little pieces, which is of course going to add up to E. Sum of all the contributions to E is the total E. And over on this end, dx, what I'm summing over, remember, was all the little bits of charge along that line of charge. And it's these dq's in here, and their positions run from 0 up to A. So the integration variable, the limits of integration are 0 to A. See, this is a constant, so I can factor it out. That's Kc times the integral from 0 to A of x prime dx prime, all divided by x minus x prime squared. Let's go ahead and I want to make a substitution. I'd rather just have a variable squared on the bottom. So I'm going to make a substitution. Let's let z be equal to x minus x prime. So this will just be z squared on the bottom. I need to replace x prime with what it is. Solving this for x prime, I get that's x minus z. And then I got to replace the dx prime. So go ahead and take the derivative here. Dx prime with respect to z is just going to be minus 1, multiply both sides by the dz, and I got dx prime is equal to minus dz. So I think I'm ready to substitute now. Let's say get the limits of integration here. When x is 0, so say z of 0 is just equal to, I'm integrating over x prime, not x. When I integrate over x prime, when x prime is 0, z is just x. And when x prime, my original variable of integration, is equal to a, I get z is equal to x minus a. So the limits of integration for my integration over z are x up to x minus a. Remember that x is the position where I'm calculating the electric field over here, and as I sum up all the little pieces over here, that position remains fixed. So x is a constant with respect to integration here. So the x prime is x minus z, and then dx prime is minus dz, and x minus x prime is what I call z to make this denominator simpler, and I get z squared there. This I can look at as the sum of two terms, two pieces. I think I'll write them in the opposite order. I'll take the minus and a minus here. So I got one term that's kc times z over z squared. That's 1 over z. dz, and then minus, that's actually this minus associated with this x term, x over z squared. I need an integration sign in there, and that's from x up to x minus a. And then you got minus x times the integral from x to x minus a. The piece in here is x over z squared. That's z to the minus 2. That's the way I want to write the over z squared dz. Once again, the x you can think of it as being in here, but I was able to factor it out because it's a constant with respect to the integration. And then the integration goes pretty easily. This is the natural log of z. Evaluated from x to x minus a. And then minus, this was supposed to be a minus 2, because it's in the denominator up here. Z squared in the denominator, same thing as z to the minus 2. So I'm integrating the power, x times z, bump that up by 1, it becomes minus 1. So z to the minus 1. And then divided by the new power, which is minus 1, so put that over there, and evaluated from x to x minus a. And that's going to be equal to Kc. It's our electric field. Times the natural log of x minus a minus the natural log of x. But the difference in logs is the log of the ratio, so I'll call that natural log of x minus a over x. And then plus, I'll have x times z to the minus 1 evaluated at x minus a, so that's x over x minus a, and then minus x times z to the minus 1 evaluated at x, that'll be x times x to the minus 1, or just 1. So E is K times C, and that will have the units of coulombs per meter squared, so this does have the units of E times this expression inside. That's the electric field. It's rightward directed. The electric field is to the right. I can actually put a unit vector I in here to make that clear. Assuming that C is a positive value, so we've actually got positive charge distributed along there, and if it's negative, this expression is still correct. Has the right units, and this is our expression for the electric field at points to the right of that linear charge distribution. And that marks the end of problem